This is Unit 2, Section 1. We're going to be talking about transformations of functions and absolute value functions. There are different families of functions. Families of functions are made up of functions with certain characteristics. A parent function is the simplest form of a function. It's the most basic function in a family. And then the functions in the same family are transformations of their parent function. Here we see three different parent functions. Many more exist, but these are three of the most basic. We have the linear family. The most basic one is f of x equals x or y equals x. Domain is all real numbers, range is all real numbers, and this would be the table of values for a linear function. An absolute value function is a type of piecewise function. The parent function is f of x equals the absolute value of x. The domain is all real numbers, and the range is y is greater than or equal to 0. You notice that we have the point here at 0, 0, so everything is going above that, y is greater than or equal to 0. Then for a quadratic function, it's f of x equals x squared. Quadratics are represented by parabolas. Domain is all real numbers, and again, the lowest point here is at 0, 0, so the range is y is greater than or equal to 0. The transformations that can occur, they will change the size, shape, position, or orientation of the graph. So horizontal translations are going to shift left and right. The transformation happens to the x value, and it's always going to end up being the opposite sign. So if we had x plus k here, that would mean we'd be moving k units to the left, right? Plus is going to mean left, minus is going to mean right. Vertical translations shift up and down. So the transformation is always going to happen to the y value. So that means it's going to happen outside of the x value or after we see the x value. A reflection is going to flip the whole graph over a line called the line of reflection. If we were to reflect over the x-axis, we're going to apply that to the y value. So it ends up being negative times f of x. A vertical stretch makes the graph more narrow. It applies to the y value, and it's considered a vertical stretch if the value we're multiplying the y value by is greater than 1. And then a vertical shrink makes the graph more wide, so that's also going to be applied to the y value, and it's considered a shrink if the number is between 0 and 1. Notice I'm only talking about positive values here because the negative value is what made it a reflection. So we ignore the negative if it happens on a number besides 1, and we focus specifically on the number itself to determine if it's a stretch or a shrink. So we're going to look at a few examples. We're going to identify the function family that the new graph belongs to and describe its transformation from the parent function. So my parent function here is in red, and this is the new function I'm looking at. So these are both linear functions, and I notice that it's x minus 4, which also means from its original spot, it moved down 4. An argument could be made that it was really x minus 4 together, in which case you could say it moved to the right 4. For linear, that's fine. You can go either way. This one looks like a V, so this one is absolute value. All right, notice it's x minus 3. Both parts are inside the absolute value bars, which means it's being applied to the x. So minus 3 means to the right 3, and we could check that here. Our vertex, or our point of the V, moved 3 places to the right. So that is the transformation from the parent function. This one looks like the U, so this is a parabola or quadratic. And there's a negative in front, and notice that it was opening up and now it opens down. That was a reflection. So you go ahead and try these three, identify the function family, and describe the transformation. Pause it and I'll show the answers. Okay, so number 1 was linear. It moved up 3 or left 3. Number 2 was quadratic, and it moved to the right 4. And 3 was an absolute value function, and it was a reflection. Here we have some more. Now we're going to talk about our stretches and shrinks. So we notice that the number outside is 2, and my new graph, the blue one, is much more narrow than the red one. So this was absolute value again, and it was a vertical stretch by a factor of 2. Right? The number in front was bigger than 1, so it was a stretch. In this next one, we have a quadratic. We're looking at parabolas. And the number in front is 1/2, which means it's between 0 and 1. So we're looking at a vertical shrink by a factor of 1/2. And notice in this one, my original was red. The blue one is much wider. So you try this one, pause it, and I'll show the answer. All right, this one was a little tricky because it was 3/2, and 3/2 is in fact bigger than 1, which makes it a stretch of 3/2. All right, now we're having a little bit of a combination of transformations. So notice that there's a 2 out front and there's a +1 afterwards. So the 2 out front reverts to a vertical stretch by a factor of 2, and it's a vertical translation up 1. All right, and this was a V, so we're going to call it absolute value again. All right, so you try this one. You could pause, and I'll show the answer. All right, so this one was a quadratic function with a vertical shrink of 1/4 and a horizontal translation 3 to the right. For graphing transformations, we're going to create a table of values for the parent function. So if you recall, we're going to focus exclusively right now on absolute value. So the parent function is going to be originally x and y, and we're going to plug in -2, -1, 0, 1, 2. And because we're taking the absolute value of all these, we're just getting the positive values back. So whatever number is with the x value, we're going to do the opposite of that to our new x values. Whatever number is after it, we're going to do exactly that to the y values. And then we're going to multiply y by either -1 or whatever the value of a is based on the number in front of the function. And then we can graph our new function. So here we're going to graph our absolute value function. I'm going to start with my parent function here. And this is going to be the same every time unless I choose to plug in different x values. If there's a fraction out here, I might choose to do some different x values. So what I'm going to do is I have x plus 2 here, and I said I'm going to do the opposite of x. So that means this column is going to become x minus 2. And whatever's outside is going to happen exactly. So that means we're going to do y minus 3. So that means we're going to take every number in my x column and I'm going to subtract 2 from it. So we get -4, -3, -2, -1, and 0, right? -2 minus 2, -1 minus 2, 0 minus 2, 1 minus 2, 2 minus 2. And now I'm going to take every value in the y column and subtract 3. So we get -1, we get -2, -3, -2, -1. If I were to graph this, we have the point -4, -1, -3, -2, -2, -3, -1, -2, and 0, -1. So this is our new function based off the original parent function, which would have been here at the origin. My domain for every absolute value function is going to be all real numbers. And notice here my range, just like when we were talking about piecewise, if there's a bottom point on the graph, we're going to have y is greater than or equal to whatever the y value was of that bottom point. And that was -2, -3 down here. So that means it's going to be y is greater than or equal to -3. Let's look at some more together. Ooh, I just realized we didn't do one of the things. Describe the transformations. So we'll go back to this. So +2 here meant we were going left 2, right? Horizontal translation, left 2, and down 3. And if I check my vertex here, if I started at 0, 0, I went to the left 2 and down 3, and that's where my new vertex was. So I did that correctly. So now we'll try this next one. Let's start by describing it. We have x minus 1 here, which means we should be going to the right one, right? It's always going to be opposite. And we have +2 outside, so that's going to be up 2. We'll start with my original parent function. And now I'm going to do opposite of inside, so that x minus 1 turns into x plus 1. Same outside, we get y plus 2. So now I'm going to add 1 to each of these. And I'm going to add 2 to each of these. So now we can graph it. There's my new function. Remember, domain's always all real numbers, and range, my lowest point, so we have greater than or equal to, was 2. Notice it should always be the middle point here. If we've picked our original points correctly, this should always be the value for our range. All right, you try this one. You could pause it, and I'll show the answer. All right, there you go. We were going to the left 3 and up 1. If we check left 3, up 1, that is in fact where our graph is. Y is greater than or equal to 1 for the range. All right, we'll focus on some stretches and shrinks here. So the number out front is a +2, so I don't really have to worry about what I choose for my parent function. Let's go back to the black. So I'm still going to keep it as my -2, -1, 0, 1, 2. Right? And what's happening is I should have a vertical stretch of 2, right? My graph should be getting more narrow. So there's nothing happening inside the absolute value bars, so it's just going to stay x there. But I'm going to be doing 2 times y. So I'm going to keep all my x's, but I'm going to double my y's. So now we have -2, 4 here, -1, 2, 0, 0, 1, 2, 2, 4. And notice this one is much more narrow than the previous ones. So domain is still all real numbers. And my lowest point here was at 0, 0. So y is greater than or equal to 0. All right, and this next one I have -1/2. So what I'm going to do is I'm going to pick numbers for my domain that are going to be divisible by 2. So I'm going to just go with -4, -2, 0, 2, 4. And remember, this is just the absolute value, so I'm going to get 42024. This is a negative, so we have a reflection. And 1/2 is a vertical shrink. So a vertical shrink of 1/2. So again, nothing's happening inside the bars, so x gets to stay the same, but I'm going to multiply y by both the negative and the 1/2. So negative 1/2 y. So I'm going to keep all those x's, but now I'm going to do negative 1/2 times this. So negative 1/2 times 4 is negative 2. Negative half of 2 is negative 1, right? Anything times 0 is 0. Negative 1/2 times 2 is negative 1, and then we get negative 2. So now I have negative 4, negative 2, negative 2, negative 1, 0, 0, 2, negative 1, and 4, negative 2. So notice this is much wider, and it's flipped over because there was a reflection. So again, domain won't change, but now my range has a high point instead of a low point. So my graph is pointing down, so now y is less than or equal to, still that middle number, right? The y value, 0. All right, this one has a combination. All we're going to do is graph it. We won't bother describing it. We'll graph it and we'll give the domain and range. So positive 2 out here, so I don't have to worry about what I choose. I do know that what's happening with the x, I'm going to do the opposite. So we have x plus 1. There's a 2 out front, so that's 2 times y, and then there's a plus 3 afterwards. So this ends up being 2y plus 3. So now all my x's, I'll add 1. And now the y's, I'm going to do 2 times 2 is 4, plus 3 is 7. 2 times 1 is 2, plus 3 is 5. 2 times 0 is 0, plus 3 is 3. 2 times 1 is 2, plus 3 is 5. 2 times 2 is 4, plus 3 is 7. So now I have negative 1, 7, 0, 5, 1, 3, 2, 5, 3, 7. So my domain was all real numbers, and my range, low point now, right, pointing up, so greater than or equal to, and the value of y there was 3. All right, try another one together. Again, I'm not going to worry about what I plug in because it's a negative 1 outside. But now I'm going to have x minus 2 and negative y plus 4, right? Negative 1, so negative 1y plus 4. So subtract 2 from all the x's. And now I'm going to take it, the y value, turn it negative, and then add 4. So negative 2 plus 4, negative 1 plus 4, 0 plus 4, negative 1 plus 4, negative 2 plus 4. So I have negative 4, 2, negative 3, 3, negative 2, 4, negative 1, 3, 0, 2. So that is my absolute value function. Domain was all real numbers, pointing down, so less than. And the highest value here was 4, right? Got that from there. One more together, and then you guys will try the last one. So now I have a 1/2 outside. So again, I'm going to pick numbers that are divisible by 2. So I'm going to go negative 4, negative 2, 0, 2, 4. You could still do this. If you chose your original numbers, you're just going to have to graph some decimals. All right, and now we're going to have x plus 2, right, opposite, and then 1/2 y plus 1. So if I add 2 to each of my x's, that's what I get. Half of 4 is 2, plus 1 is 3. Half of 2 is 1, plus 1 is 2. We get 1, 2, 3. So when I graph, I'm going to get something that looks like this. Again, domain is all real numbers. It's pointing up, so my range is greater than or equal to, and my y value was 1. All right, you're going to try the very last one. You could pause it, then I'll show the answers. Ooh, wow, that was bad, guys. All right, domain was all real. Range was y is less than or equal to -1. All right, and that is graphing transformations and absolute value functions.